Hello everyone, my name is Arnav and today we'll be doing the 2023-2024 Virtual Challenge Meet number 3 for UIL Science. Today we're going over the physics section, and before I start the section, I would like for you guys to try out the test on your own to make sure you guys can get a feel of all the questions. These are the questions from numbers 1 through 7. These are the questions from number 8 through 13. And these are the questions from number 14 through 20. Here, and there's also the formula sheet if you guys want to see all the constants that you'll be given on the test. Now I'll get started by answering all the questions on the exam. For the first 3 questions on the exam, you're going to be given a reading, and the answers to the question for the first 3 questions is straight from a reading, and the reading changes each year. This year's was 5 Equations That Changed the World by Michael Gillen. So the answers to number 1 is going to be A, Archimedes. The answer to number 2 is going to be C, continuity. And the answer to number 3 is going to be E, Leonard Euler. Number 4. The largest known volcano in the solar system is the Olympus Mons volcano, a 27-kilometer high shield-type volcano on what planet? This is just something you have to know off the top of your head. The answer is going to be Mars. Olympus Mons is the largest volcano in the Milky Way, and it's located on planet Mars. 4th question will always be an astronomy question, so the answer to number 4 is going to be letter D. Number 5. The primary standard of mass for our country is the United States prototype kilogram 20, which is a blank cylinder kept at the National Institute of Standards and Technology, located in Gatesburg, Maryland. Number 5, the answer, kilogram 20 is a platinum iridium cylinder that is located in Gatesburg, Maryland. So the answer to number 5 is going to be letter B. Number 6. Tony was driving on the Fort Bend freeway at a constant speed of 20 meters per second. Several cars honked at him, so he uniformly accelerated for 7 seconds until he reached a speed of 34 meters per second. He then drove at a constant speed of 34 meters per second until he got off the freeway at the College Station exit. How far did Tony travel during the 7-second acceleration? So initially, let's define our variables first. On any of the physics problem, you want to start with the variables. Initial velocity is going to be 20 meters per second. Final velocity is going to be 34 meters per second. That's given to us in the problem. The time for acceleration is 7 seconds. So we want, and what do we want? We want to find the displacement, how far the car traveled in the time frame. So there are 2 formulas we can use called kinematic equations. These are the 2 formulas we can use. The displacement equals the initial velocity times time plus 1/2 times acceleration times time squared. That's one formula. The other formula we can use is final velocity squared equals initial velocity squared plus 2 times acceleration times displacement. Just get rid of, These are the 2 formulas you can use. I'll go over both of them when solving this problem. First formula, we want to find displacement. We're given initial velocity as 20. We're given time as 7 seconds. 1/2. How do we find acceleration? Acceleration is equal to change in velocity over change in time. Velocity went from initially 20 to 34. So 34 minus 20 is the change in velocity. It's the difference between initial and final velocity. And all this happened in a change of 7 seconds. So 34 minus 20 is 14. 14 divided by 7 is going to be 2. That's the acceleration. And then time squared is 7 squared. Plugging everything in, you would be getting 189 meters. The other formula, final velocity is 34 squared, initial velocity is 20 squared, plus 2 times acceleration we calculate as 2, and displacement. Solving for displacement, 34 squared minus 20 squared divided by 2 you would get 189 meters. So the answer, using either method, you would get the same number as 189 meters. So the answer to number 6 is going to be C. Number 7. A wooden block is given a push so that it slides across the classroom floor. The push imparts an initial speed of 3.13 meters per second. If the coefficient of sliding friction between the block and the floor is 0.285, how far would the block travel before it comes to rest? This is another, looks to be a kinematic problem, but let's draw out the diagram. You have the block. It's standing on a flat surface. So if we've seen previous videos, you know that if an object is on a flat surface, their weight and their normal force are equal. So weight equals normal force. So what are all the values we have? We know the initial value is 3.13. The initial velocity is 3.13. And the coefficient of friction is 0.285. We want to find displacement, again, just like the last problem. So what are some ideas we can use? Well, we know that because there is friction. Friction is a force. Friction, like if the object was moving, what's the blue arrow? The object was moving with the velocity, there would be friction on the opposite direction because friction opposes motion. So if you're moving to the right, friction will make you move to the left. So what are all the forces we have? Velocity is not a force. Velocity is just the general direction of movement. These are all the forces we have. Normal force, weight, and friction. Normal force and weight cancel each other out because weight's pointing down, normal force pointing up. So these two cancel each other out. But friction is net force. The net force on this block is friction. So what is the formula to find force of friction? That's the coefficient of friction times the normal force. And we know since normal force equals weight and weight equals mass times gravity, this is essentially normal force times mass times gravity. So what formulas can we derive from that? Well, we know net force, according to Newton's second law, is mass times acceleration. We know since net force equals the friction force, mass times acceleration equals the coefficient of friction times mass times gravity. So the mass cancels out. The acceleration is equal to the coefficient times gravity. So plugging the values in, 0.285 times 9.8. And plugging that into a calculator, you would get acceleration to be equal to 2.793 meters per second squared. That's the acceleration on the object. So we can find acceleration is equal to 2.793. Now we're given one more key value. How far will the block travel before it comes to rest? So at the very end, the block is resting. What does that mean? That means the final velocity is equal to 0. So these are all the values we have that we need to solve this equation. We're given, well, we don't need the coefficient of friction anymore, actually. We're given initial velocity, acceleration, final velocity. So using the kinematic equation, final velocity squared equals initial velocity squared plus 2 times acceleration times displacement. We can solve for displacement. Final velocity we know is 0 because the object's coming to rest. Initial velocity we know is given to us as 3.13. Acceleration we calculated. And displacement is what we're trying to find. So doing the math. Also, wait, one more thing. Acceleration is actually negative because it's opposing motion. The object's going to the right, yet the friction is pointing the opposite direction. So the object is decelerating. So this would actually be negative 2.793. So change that up a little bit here. Make sure that's negative So now solving for displacement, you would get negative 3.13 squared divided by 2 divided by negative 2.793. You would get displacement equals 1.754 meters. So the answer choice closest to 1.754 is going to be A, 1.75. So the answer to number 5 is going to be letter A. Number 8. Joseph drove from Groover to the Canadian River Bridge. He attached one end of a bungee cord to the bridge and the other end to his ankle and jumped off the bridge. Joseph fell 18.2 meters before the cord began to stretch. The bungee cord obeys Hooke's law with K equaling 55.5 newtons per meter. How far below the bridge did Joseph fall before coming to a stop? Ignore the mass of the cord and air resistance. So, like any other physics problem, let's diagram what's going on. You have the bridge. You have Joseph with his cord. And he fell. So, let's read the problem. He fell 18.2 meters before the cord started stretching. So, the 18.2 meters is just the cord at its natural length. After a certain point, it started to stretch by a certain, let's call it X meters. So we're trying to find, so what are we trying to find? We're trying to find the total, how far did Joseph fall before coming to a stop? He stopped at this black point right here. So that means we're trying to find X plus 18.2. That's what we're trying to find. So this problem relates to the law of conservation of energy. In fact, the 8th question usually has to deal with conservation of energy or conservation of momentum. So that's like a tip if you're having trouble with that one. Just try to see if you can use either of those. So here, conservation of energy means that the total energy before equals the total energy after. So energy before. I'd say energy before is when Joseph was still on the bridge, before he jumped. What kind of energy did he have? He was not moving, but he had an elevation. Let's say that this green line here is the ground floor. This is 0, where height is equal to 0. When Joseph's on the top of the bridge, he has this elevation right here. He has X plus 18.2 meters of elevation. So that's his height. Remember the formula, and so that means he has to have potential energy. Remember the formula for potential energy is equal to mass times gravity times height. Gravitational acceleration constant times mass times height. So what about after he jumped and once he reached this point over here? Once he reached the black dot. Does he have potential energy? Gravitational potential energy. Remember, the green line is the ground floor. Green line means no height. So he has no height, so he has no potential energy. He has no gravitational potential energy. And since he stopped at the bottom, he has no kinetic energy. But he does have elastic potential energy because he has a bungee cord. The bungee cord stores elastic potential energy. And the formula to find elastic potential energy is 1/2 times the elastic constant times the displacement of the rope squared. So X is, in this case, is the displacement of the rope. It's the length of the rope at natural length minus the length of the rope at stretched or compressed length. So we want to equate these to each other because that's what the whole law of conservation of energy equals. Total energy before equals total energy after. Plugging in values, let's see what we get. We know the mass of Joseph, 77.1. Gravitational potential energy on Earth is 9.8. Gravitational constant is 9.8. The height of the bridge is X plus 18.2 compared to the green line we drew. K is given to us as 55.5. And X is what we're trying to find. So this is the equation we have now. I'll make this period look neater. This is the equation we have. right there. So this is now just good old quadratic equation. So if we get everything to one side, 55.5 divided by 2, you get 27.75 x squared. Let's go backtrack a little bit. 75 x squared minus 77.1 times 9.8. 755.98x minus 13,751.556 equals 0. This is the equation in standard form. And now using the quadratic formula, and we're trying to solve for x. So 755.58 plus or minus the square root of 755.58. Actually, this is a 558 squared minus 4 times 27.75 times negative 13,751.56 over 2 times 27.75. Quadratic formula right here, where you plug in all the values that we have. And solving, and this all equals x. Solving for x gives you 39.708 meters. That's the value for x. But we're not trying to find x, are we? We're trying to find the total height of the bridge. We're trying to find x plus 18.2. So x plus 18.2 equals, so we're plugging that plus 18.2. You would get 57.908 meters. That is our final answer. 57.908 is closest to letter D, 57.9. So the answer to number 8 is going to be letter D. Number 9. Aiden brought a new computer from Toller Electronics. The platter of the hard drive rotates at 6,000 rotations per minute. If the disk took 3.33 seconds to spin up to 6,000 rotations per minute, what is the average angular acceleration? So this is very similar to the kinematic problems back in the first few, except now we're doing the angular acceleration, not linear acceleration. But the concepts are very similar. The concepts for angular and linear acceleration, they're very similar. We use the symbol, you might be familiar with V for velocity. Use the symbol omega to describe angular acceleration. Angular velocity. So, what was the initial angular velocity? Well, if the disk took 3.33 seconds to spin up to 6,000 rotations per minute, we can assume that the initial angular velocity was 0 rotations per minute, and that the final angular velocity was 6,000 rotations per minute. And we know the time it took was 3.33 seconds. But we're seeing something wrong here. First of all, look at the answer. Look at what the answer has to be in. Radians per second squared. Look at what time we're given. Seconds. And then look at the units. Rotations per minute. We need to convert everything around. We know 1 rotation is equal to 2 pi radians. Because 1 rotation is 1 whole circle, and there are 2 pi radians in 1 whole circle. And we obviously know that there are 60 seconds in a minute. So we can convert each of these. So, the first one for initial velocity will stay 0. It would still say 0 radians per second because 0 times anything is going to be 0. The second one, 6,000. Let's convert that into rotations per radians per second. Radians per 1 second. So how many radians are in one rotations per minute. Forgot, one sec. So how many radians are in one rotation? There are 2 pi radians in one rotation. And how many seconds are in a minute? There are 60 seconds in a minute. So we can cancel out rotations, we can cancel out minute. We're left with radians per second, which is what we want. So 6,000 times 2 pi divided by 60. You're going to get 628.32 radians per second. That's the final velocity. Now, plugging in the formula for, well, if you guys can't remember the angular acceleration formulas, just remember the linear acceleration ones. Remember, linear acceleration is change in velocity over change in time. So, angular acceleration, which is denoted as a symbol alpha, is the change in angular speed over time. Change in angular speed is 628.32 minus 0, because initial was 0, final was 628.32. And this took place in 3.33 seconds. So, doing the math, you would get 188.684 radians per second squared. So radians, this is the final answer. 188.684 radians per second squared rounds closest to 189 radians per second squared. So the answer to number 9 is going to be E. Number 10. A 36 centimeter long organ pipe is closed at one end. Find the frequency of the third overtone if the air temperature is 20 degrees Celsius. Well, what do we know about, let's list all the values we have right now. We have the length of the pipe, which is 0.36 meters. We know that it's closed, so there's a certain set of formulas we need to find if it's closed. We're trying to find the third overtone of a closed pipe when the temperature is 20 degrees Celsius. Let's go over the easier part first. What is the speed of sound when the temperature is 20 degrees Celsius? The speed of sound, the formula to find the speed of sound given temperature is equal to 0.6 times temperature plus 331. That means the speed of sound is going to be 0.6 times 20 degrees Celsius. And yes, it doesn't have to be in Kelvin. This is one of the few equations where you do not need Kelvin. In fact, it's out. You'll get it wrong if you put it in Kelvin. So yeah, keep it in Celsius for this one. Here, we know the speed of sound is 343 meters per second. Now we want to find, what are we trying to find? We're trying to find the frequency. So we know that the wavelength of a wave times the frequency of the wave equals the speed of the wave. We know the speed of the wave. We know the speed of sound. We're trying to find frequency. So we can rewrite the equation as something like this. Frequency equals speed divided by wavelength. So we know speed, we're trying to find the wavelength now. In a closed organ pipe, which is when you have one end that's open and the other end that's closed. In a closed organ pipe, the formula to find the wavelength is equal to 4 times the length of the pipe divided by the overtone, or the mode of frequency, the mode of vibration. So what's the length of the pipe? We know the length is going to be 0.36. What is the mode of vibration? In an open pipe, the mode of vibration is just 1 plus the number of overtones. So in this case, the third overtone would be 1 plus 3 would be and would equal 4. In an open pipe. In a closed pipe, it's not the case. In a closed pipe, you would find 1 plus 2 times the overtones. So there's 3 overtones, a third overtone. So 1 plus 2 times 3 would equal 7. So the harmonic number would equal 7. So the wavelength is equal to 4 times 0.36 divided by 7. So 4 times 0.36 divided by 7 would equal, wavelength equals 0.206 meters. That's the wavelength. Plugging everything in, 343 over 0.206. Plugging that in and solving, you would get 1,667.36 hertz. So the answer is going to be 1,667. So number 10, the answer is 1,667 hertz. Number 11. Dr. Verby gave Laney special permission to hunt on the Isaac Ranch. She accidentally fired a stray bullet that made a hole in a full water storage tank. The tank is shaped like a cylinder with a diameter of 3 meters and a height of 6 meters. The hole formed by the bullet was located 20 centimeters from the bottom of the tank. Find the speed of the water leaving the hole, right after leaving the hole. Let's draw the situation here. We have a cylindrical tank. I'll draw it as a rectangle for this point of view. It is filled with water. The rectangle tank is also 6 meters tall. 6 meters tall. And there's a bullet that struck it. I'll draw this green spot as the bullet hole. This bullet struck it at 0.2 meters above the bottom, because 20 centimeters is the same thing as 0.2 meters. Water is flowing out of that bullet hole down. So it's asking us to find the velocity right at the bullet mark where the bullet hit. So I'll draw the red line as the normal line, the ground, pretty much the ground level. So at ground level, there's 0, the height is equal to 0. This problem is related to the law of conservation of energy, where the sum of all the energy before equals the sum of all the energy after. Sum of energy before equals sum of energy after. So what's the energy before and what's the energy after? At the very beginning, the water is at the very top of the tank. What kind of energy is located at the very top? The water's not moving, but the water has altitude because it's high. It's high from the ground. So the water only has potential energy. What about at the very bottom? Well, maybe not at the very bottom, but at the bullet hole. Is the water above the ground line? It is above the ground line, so it does have potential energy. But what else does it have? Since the water is closer to the bottom, it's actually going to be exiting at a specific rate. It's going to be moving at a rate. That's called efflux, when a fluid is moving, a moving fluid that's leaving a tank. So because the fluid is moving, it would have kinetic energy. So at the very top, it only has potential energy. At the bottom, it has potential and kinetic energy. So energy before is potential energy 1. Energy after is potential energy 2 plus kinetic energy. That's a kinetic energy 2, but even though there's only 1 in this problem. So what's potential energy 1? What is the formula for potential energy? Potential energy is equal to mass times gravity times height. There is one big thing you have to know, is that this is only true for solids. For liquids, it's a bit different. For liquids, it's density. Actually, for any fluid, so even for gases. For fluids, it's density times gravity times height, where P is density. So that's the same thing for kinetic energy. Initially, it's 1/2 mv squared, But for fluids, it's going to be 1/2 PV squared, density times velocity squared. In this problem, it does not matter at all, and I'll show you why soon. But this is good to know for future problems relating to fluids. When it comes to fluids, you use density and not mass. So what is PE1? That's density times gravity times height 1. Which actually I'll plug all the values in. So actually at the end, because I'll show you why density is not relevant. Like knowing that density times gravity times height is irrelevant for now. This is the final answer you get when you break everything down into potential and kinetic energy. Density is on each and every term, so you can actually divide both sides by density. You're only going to be left with gravity times height 1 equals gravity times height 2 plus 1/2 velocity squared. What is height 1 and height 2? Height 1, I'm going to diagram in brown, this green line, the ground line. Height 2, I'm going to diagram in green, this green line I just drew. So height 1 is going to be 6 meters. Height 2 is going to be 0.2 meters because that's where the bullet point is, 0.2 meters above the surface. And we're trying to find velocity. So plugging in everything, solving for velocity, 9.8 times 6 minus 9.8 times 0.2 times 2 square root of the answer. You would get 10.662 meters per second. That is rounding up to be 10.7 meters per second. So the answer to number 11 is going to be letter B. Number 12. Find the voltage drop across the 90 ohm resistor. So let's first start by using Ohm's law. Voltage equals current times resistance, total resistance. We're given voltage is 60. We want to find current first. That's how we find the voltage drop. And we can solve for total resistance. Let's examine this circuit first. You have 150 ohm with a 90 ohm. In a parallel circuit, because this is clearly a parallel circuit since both of these lines are parallel to each other, you can use the formula 1 over total resistance equals 1 over resistor 1 plus 1 over resistor 2. So 1 over total resistance equals 1 over 150 plus 1 over 90. Solving for that, total resistance for this specific set is going to be 56.25 ohms. So we can actually replace this whole thing, actually just replace everything here with our newfound resistance, which is 56.25 ohms. I'll change it to black. Bring that down. This is going to be 56.25 ohms. Let's do the same thing for the second this set right here. So you have 120 ohms on one side, 180 ohms on the other side. 1 over total resistance equals 1 over 120 plus 1 over 180. 1 over 120 plus 1 over 180, 1 divided by the answer. Total resistance would equal 72 ohms. So we can replace this segment with a 72 ohm resistor. 72 ohms. Now you only have 2 resistors in series. In a series circuit with resistor 1 and resistor 2, to find the total resistance, you just add them up. Resistor 2. So in this case, total resistance will be 56.25 plus 72. total resistance would be equal 128.25 ohms. That's the total resistance right there. So essentially what that means is, oopsies, it's fine. That essentially means that these two circuits are completely replaced with one resistor. It is equivalent to having one resistor of resistance 128.25 ohms. Now we can use voltage equals current times resistance. Let's move everything up here a little bit. Save space. Voltage is 60 volts. We're trying to find current. And we know resistance is going to be 128.25. So what is current? The current flowing through the circuit is going to be 0.468 amps. So that means I'll draw in red. Remember, if it goes from positive to negative, the current is equal to 0.468 amps. So what is it asking though? It's asking to find the voltage drop across a 90 ohm resistor. So let's quickly erase everything we did right here. Now that we know what the voltage is, we actually don't need to know, we don't need to solve all that. We want to find the voltage drop across this resistor. Now we need to know properties of series and parallel circuits. I'll draw it down here. In a parallel circuit, actually I'll draw a series circuit first. In a series circuit, voltage drops, or I'd say voltage changes per resistor. Or I mean, instead of each resistor, I'd say depending on the resistance value. Changes on the resistance. But current stays the same throughout. That's in a series circuit. Parallel circuit, Parallel circuit, it's the exact opposite. It's current that changes based on the resistor and voltage that stays the same throughout in a parallel circuit. So replace this with parallel. So how does that help? 90 ohm and 150 ohm are in a parallel circuit, parallel segment. So we need to use the parallel resistor properties. We know that the current changes depending on resistor, and we're trying to find the voltage drop. Voltage equals current times resistance. We're given the resistance of 90 ohms equals current times 90. We're trying to find the current. What's the current on the 90 ohm resistor? Well, we know that changes depending on the resistance. Voltage is staying the same, but the current is changing. So we know that the current that enters here, we can separate that as I1 and as I2. Based on the law, Ohm's law, we know that current and resistance have to be inversely proportional. As resistance increases, current decreases. If I draw it like here, the higher your resistance, the lower your current. So that means the one with 150 ohms has to have the lower current. The lower current. The one with the 90 ohms has to have the higher current. So we can draw a ratio. We can draw X and Y. X over Y equals not 150 over 90, because X has to be lower than Y. So that means that would be 90 over 150. X over Y equals 90 over 150. And we know X plus Y equals 0.468. So with that in mind, solve for x and solve for y. We want to find y. That's what we're trying to find. So let's go over the scratch paper. So x over y equals 3/5, simplifying it. And x plus y equals 0.468. X. So that means x equals 3y over 5. 3y over 5 plus y equals 0.468. And then just doing some algebra to get the value for y. So y equals 0.468 divided by 0.6 plus 1, 0.2925 amps. That's the current that's flowing through the 90 ohm resistor. We're trying to find the voltage. So voltage equals current times resistance. Current is 0.2925. Resistance is 90. You would get 26.325 volts. So the answer is going to be A, 26.3. Number 13. A point charge of 240 nanocoulombs is placed at A, and a point charge of negative 300 nanocoulombs placed at C. Find the net electric potential difference at point B. So, we're trying to find the net electric potential difference. What formula would we use for that one? First of all, let's derive it. We know voltage is equal to work divided by charge. So we want to find the net potential difference, or essentially the voltage. We know that work is equal to force times displacement over charge. And magnetic force, electromagnetic force, is Coulomb's law. We would use Coulomb's law. K times Q over R squared. So you get K times Q, charge, Q and capital Q, lowercase q, if you haven't watched my other videos, is the charges, are the charges. So Coulomb's constant times charge 1 times charge 2 over the distance between the charges squared times the distance between the charges. We can actually replace D with R because we're looking at the same value, distance between the charges, over Q. Solving for everything, you would get KQ over R as the voltage between voltage on charge. So now using this formula, voltage equals Coulomb's constant times the charge of the point divided by the distance between the points. Let's find the voltage that A puts on B. That is equal to K, which we'll put K, if you haven't know, K equals 8.99 times 10 to the power of 9. We'll put that in later. Times the charge is going to be 240 times 10 to the power of 9, negative 9, because it's nanocoulombs. Divided by the distance between A and B, which is going to be given as 0.09 meters. So plugging everything in, 8.99 times 10 to the power of 9 times 240 times 10 to the power of negative 9 divided by 0.09, you're going to get 23,973.33. What voltage from B to C? It's K times the charge, which is, in this case, it's negative 300 times 10 to the negative 9 over, what's the distance between B and C? 0.12. So plugging everything in, you would get negative 22,474. Notice how this time I put signs on. When it comes to voltage, you want to keep your signs this time. In my previous videos, I mentioned how you can ignore the signs. That is only for electromagnetic force, and that's only for electric fields. For this question, you want to keep the sign in. So this would be, and both of these are in volts. So what is voltage? Here's one main thing you want to know, is that voltage is a scalar property. If it was a vector, you would have arrows like this. And if you watch my other videos, you would know that you'd get a vector triangle like this. So you'd be using the Pythagorean theorem. But voltage is a scalar, so you just add scalars. You don't need to know direction. So for scalars, if you want to find the net voltage, you just add everything. So just add the two numbers you got. You would get 1498.33 volts. So the final answer for number 13 is going to be letter C, 1500, because that's the closest to 1500, because that's closest to 1498. So the answer to number 13 is going to be C. Number 14. An electron is traveling horizontally at the speed of 5.96 million meters per second when it encounters a 1.33 Tesla magnetic field oriented vertically upwards. The electron begins to travel in a circular path at a radius of blank micrometers. So let's draw out this situation. We have an electron, and there's a magnetic field on the electron. Actually, before that, the electron is moving horizontally. There's all of a sudden a magnetic field on this electron. Let's draw that down here. There's a magnetic field on the electron. So because of that, the electron starts to move in a circular path. We're trying to find the radius of the circular path. That's our objective. So let's try to find the forces on this electron. When you add a magnetic field to a charge, there's going to be an electromagnetic force on it. So I'll draw that in green. Actually, not in green. Just keep it in black. There's going to be an electromagnetic force on it. So what is the formula for electromagnetic force? Well, magnetic force is equal to the current times the length of the wire times the magnetic field times sine of the angle. I'll actually diagram what I mean by that. So force in newtons, I is current in amps, L is length of the wire, B is magnetic field in teslas, and theta is the angle between magnetic field and wire. So when you have a wire, you have current flowing through it. If you have a magnetic field that goes through this wire, there's going to be a magnetic force that is exerted. There's going to be a magnetic force that actually it's towards an attractive electromagnetic force that's running, depending on the direction of the current. You would find that obviously using the right-hand rule, but like in this case, it would go out of the page. So it would actually be, it would be dots. The force would be out of the page. But aside from that, theta is the angle between the magnetic field and the current. But there's just one problem here. We know the current is the flow of electrons, the flow of charged particles. But we're not trying to find current through a wire. We're trying to find one particle. How do we rewrite this equation to show the force that is applied by one particle? we can use these two equations. Current is equal to charge divided by time, and distance is equal to speed times time. Plugging both of them in, L is, by the way, distance. You can replace length and distance the same. We can replace that with Q over T times L, which is essentially Vt, times B sine theta. T's cross out, you can get B QV sine theta. That is the final that's the main equation we need. Force equals magnetic field times the charge of the particle times the speed of the particle times the sine of the angle between the magnetic field and the speed of the particle and where the particle is moving. So in this case, where is the particle moving? It's moving horizontally, and the magnetic field is vertical, meaning the angle between the magnetic field and the velocity is 90 degrees. So theta equals 90 degrees. So this would be BQV sine of 90, which is just going to, sine of 90 is just 1. So we can actually eliminate sine of theta. So force equals BQV. We know net force in a rotating object is the centripetal force. And centripetal force, the formula for centripetal force is mass times velocity squared over the radius. So I'll draw that in brown. Centripetal force is essentially the net force of a rotating object towards the center. So you have these two equations. Let's bring this whole thing down. So BQV equals mv squared over r, because the net force is the only force applied on the electron is the electromagnetic force. So essentially the net force equals the electromagnetic force, because net force equals the only force that's available. So you can divide velocity to both sides of the equation to cancel out velocity here and remove the square. So you can get BQ equals mv over r. We want to find the radius, so we can isolate the r, so mv over bq. That's the formula we want. We have everything we need to solve this. So r equals mv over bq. We have everything we need to solve this equation. Mass. We're given that it's an electron, so we can use the formula sheet. Using the formula sheet, electron mass is given as 9.11 times 10 to the negative 31 kilograms. We're given the velocity as 5.96 million. We're given the magnetic field as 1.33 teslas. And we're given the charge of an electron on the formula sheet. The charge of an electron is known as the fundamental charge. So 1.602 times 10 to the power of negative 19. So plugging everything into the equation, you would get the radius equals 2.548 times 10 to the negative 5 meters. That's the answer. That's the radius. However, we want the radius in micrometers. There's 10 to the power of 6 micrometers per every meter, for every 1 meter. So we can convert 2.548 times 10 to the negative 5 meters into micrometers to get 25.48 micrometers. So the answer to number 14 is 25.48, which rounds up to D, 25.5. So the answer to number 14 is going to be D. Number 15. A transformer in Grandpa's tape recorder reduces 120 volts to 9 volts. The secondary contains 90 turns and the tape player draws 600 milliamps. Find the current in the primary. So this is a transformer question. What do transformers do? Transformers are there to increase or decrease voltage in alternating current. So the way transformers work is, okay, I'll just draw a basic transformer here, is they use the number of coils on both sides. Let's just say there's 2 coils on one side and 4 coils on the other. I'll actually draw that neater. 1, 2, 3, 4 coils on the other side. If there are more, current enters the left, exits the right. Since there are more coils on the right side, the voltage increases. So the formula, like the main formula you want to find for transformers is number of coils in the primary. Primary is the left side and secondary is the right side. Number of coils in the primary divided by the number of coils in the secondary equals the voltage of the primary divided by voltage of the secondary equals the current of the secondary divided by the current of the primary. So let's solve for this. We know that voltage in the primary equals 120, voltage in the secondary equals 9. We know current in the secondary is, not current. The number of coils in the secondary equals 90, and the current in the primary is 600 milliamps, or 0.6 amps. This is all we found from the question itself. So find the current in the primary. Oh wait, no, the tape player draws. Oh, never mind. This is a current in the secondary. This is current in the secondary. So find the current in the primary. So we just set up this equation. We know the voltage in the primary is 120. The voltage in the secondary is 90. The current in the secondary is 0.6. We want to find the current in the primary. So solving for that would equal the current in the primary would equal 0.045 amps. We want our answer in milliamps. So we multiply this. To convert amps to milliamps, you multiply by 1,000. So you would get 45 milliamps at the very end. So the answer number 15 is going to be B, 45 milliamps. Number 16. A double convex lens has a surface radii of 36.2 centimeters and 42.8 centimeters. If the index of refraction of the lens is 1.56, what is the focal length of the lens? For this question, you need to know this formula. 1 divided by the focal length equals the index of refraction minus 1 times 1 over the first surface radii plus 1 divided by the second surface radii. So plugging in all our values, 1.56 minus 1 times 1 over surface radii 1 is going to be 0.362 meters plus 1 over 0.428 meters. Plugging everything in, you would get focal length equals 0.3502 meters, which is 35.02 centimeters. So the answer to this question is going to be B, 35 centimeters. Number 17. Consider the Bohr model of an atom of hydrogen. Determine the wavelength of the photon that is emitted when an electron drops from the n equals 5 energy level to the n equals 2 energy level. For this, we need to know the Rydberg equation. The Rydberg equation states that 1 divided by the wavelength of a photon equals a Rydberg constant times the atomic number of the photon squared times 1 minus the final energy level squared minus 1 over the initial energy level squared. So, what are we given? We're given the initial energy level is equal to 5. The final energy level is equal to 2. We know that this is a hydrogen atom, so that atomic mass is equal to 1. And we're given the Rydberg equation, the Rydberg constant on our formula sheet. The Rydberg constant is 1.097 times 10 to the power of 7 meters to the negative 1. This is by far the most important thing you have to worry about. There is another Rydberg constant out there. I don't remember it off the top of my head, but the unit is going to be in joules. This is solving for energy equals Rydberg times z squared times 1 over nf squared minus 1 over ni squared. This is, with this Rydberg constant, you would have joules at the end instead of meters to the negative 1. Make sure, since you don't have that Rydberg constant, you want to use this formula. One sec, whoopsies. You want to use the formula I showed initially. You don't want to use the second one because you're not given the Rydberg constant in joules. You're given it only in meters to the negative 1. So that's just that. So using the Rydberg equation, we can find the wavelength. Equals 1.097 times 10 to the power of 7 times 1 squared times 1 over 4, or I'll just write it as 1 over 2 squared minus 1 over 5 squared. Plugging everything in, you would get wavelength equals 4.3341 times 10 to the power of negative 7 meters. That's the wavelength. But we're not trying to find the wavelength. We're trying to find... Oh, my bad. We are trying to find the wavelength. So that's in meters, but there's one problem. All the answers are nanometers. So we want to convert meters to nanometers. We'd multiply by 10 to the power of 9. So multiplying this number by 10 to the power of 9, you get 434.1 nanometers. So the answer to number 17 would be A, 434, because there's going to be 10 to the 9 nanometers in 1 meter. So the answer to P17 is going to be A. Number 18. What is the quark combination of a proton? Quark combination is where there's 3 different quarks and each of them have certain spin values. We want to find the spin values that add up to 1 because a proton has a +1 charge. Now normally you can memorize this, but I mean in this case, if you know that up quarks have a spin of 2/3 and down quarks have a spin of -1/3, we know 2 ups plus 1 down would equal 4/3 minus 1/3, which would equal +1. So that means you would use 2 up quarks and 1 down quark. So the answer to number 18 is going to be E, UUD. Number 19. Sashi was doing a lab in which he attached various weights to a vertical spring, pulled down the weight and released it, and then carefully timed the period of vibration. His data is plotted on the graph above. Find the spring constant used find the spring constant of the spring he used. The formula for period on a spring is going to be 2 pi times the square root of the mass of the spring divided by the spring constant, where T is the period in seconds. Remember, period is how long it takes for one oscillation to occur. M is mass in kilograms. Mass is always going to be in kilograms. K is spring constant. We can rearrange this equation to be in terms of K. So we can do t over 2 pi equals square root of m over k. T squared over 4 pi squared equals m over k. And then we can rearrange that as k equals 4 pi squared m over t squared. That is the rearrangement of this first equation that we drew. So now what do we need? We want to find k, and we're given a chart. So we can pick any of these points and plug it into this equation to get the answer. I'm going to go with this point in blue because it looks like the easiest one to use. It's just 1, 1. 1 kilogram, 1 period. 1 second of period. So if the mass is 1, so 1, 1, if the mass is 1 and the period is 1, that means k is just equal to 4 squared. So that means not the period, the spring constant is equal to 4 pi squared, which is equal to 39.478, which is equal to 39.5 rounded up newtons per meter. So the answer to number 19 is going to be D, 39.5. Number 20. Consider the LRC circuit, series AC circuit shown above. The frequency of the power source is 600 Hertz. Find the voltmeter reading across the inductor. So this is an AC circuit, so we'll have to be using a lot of different terms that most of you haven't heard of if you have just done the DC circuits. So we're trying to find what are we trying to find? We're trying to find the voltmeter reading across the inductor. What it's essentially saying is that we're trying to find the volts of this right here. So let's actually define what each of these are. Whenever you see these zigzag lines, that's talking about the resistor. Whenever you see these loops, that's talking about the inductor. And when you see these parallel lines, that's talking about a capacitor. So how do we find the voltage across the inductor? Do you guys remember Ohm's law, which is voltage equals current times resistance? What if I told you that the inductors and capacitors also have something called reactance, which works very similar to resistance? It's known as reactance. There is both inductive reactance, which is reactance in an inductor, and capacitive reactance, which is reactance in a capacitor. Remember, reactance is essentially resistance, very similar resistance. In fact, they both have ohms as a symbol. I cannot draw the ohm symbol properly, so yeah. But essentially, reactance is resistance, but for inductor, for a capacitor. So if you want to find the voltage across the inductor, you'll need to find the current times the resistance across the inductor, which is also known as the inductive reactance. This formula, we will save this formula for later because we need to know that. So how do we find XL? Inductive reactance is written as this formula. 2 pi times the frequency times the inductance, where F is frequency in Hertz, L is inductance in henries, F is frequency in Hertz. So plugging that in, so that's one formula I'll shade in red. That's the formula you will need to know. XL equals 2 pi times the frequency 600 times the inductance. Inductance is on the inductor, 36 millihenries. 36 millihenries is the same thing as 0.036 henries because milli means divided by 1,000. So this would equal 2 pi times 600 times 0.036, which is 135.717 ohms. That's This right here is the inductive reactance. So now we know the inductive reactance. But how do we find current? Because we need to multiply both if we want to get the voltage. Well, remember again, we're going to be using variations of this formula a lot. Ohm's law, voltage equals current times resistance. But we're actually not going to be multiplying by resistance. Because remember, resistance is just the resistor. We don't want just the resistor. We want to find combining all three resistances. But how do we combine all three? Is it just adding the resistances? Are we just adding the reactance of the capacitor, reactance of the inductor, and the resistance? There's a specific term for this. It's called impedance. This is what we'll be using for instead of resistance for Ohm's law. Before I get into impedance, I actually want to define what the inductive capacitance is. I mean the capacitive reactance. Capacitive reactance is equal to 1 over 2 pi times the frequency times the capacitance. Another formula you will need to know. On top of V equals IR, V equals IZ, and V equals I times the inductive reactance. Let's move V equals IZ later, and I'll go more in depth what exactly that is. For now, let's try to solve for capacitive reactance. So XC equals 1 over 2 pi times 600 times capacitance is 18 microfarads. 18 times 10 to the negative 6, because micro is times 10 to the negative 6. So plugging everything in, you can get 2 times pi times 600 times 18 times 10 to the power of negative 6. 1 divided by the answer, you can get 14.737 ohms. That's the capacitive reactance. Why do we need this? It's to solve for impedance, which is what we're trying to find here. There's this right triangle. This is honestly the nicest method I use to memorize the formula. Where theta is the phase angle. You won't need it for this question, but maybe in future questions you might need it. But theta is going to be the phase angle, which is essentially the difference between the angles in radians between sine waves in an AC current, which you don't need to know in this question. So moving this down, the opposite will be the difference between the reactances. The adjacent will be the resistance, and the hypotenuse will be the impedance. So Pythagorean theorem states that resistance squared plus inductive reactance minus capacitive reactance squared equals impedance squared. That's straight from this triangle, Pythagorean theorem. Solving for impedance, we can get this formula. This is another formula you'll need to memorize. I think this might be the last, but this is the last formula you'll need to memorize for this question. Impedance equals the square root of the resistance squared plus inductive reactance minus capacitive reactance whole squared. Weird formula. So let's move this part up here. What is Z? Z equals the square root of the resistance, which is 240 squared, plus the difference between inductive and capacitive reactance. So inductive reactance is 135.717. Capacitive reactance is 14.736. Plugging everything here. You would get an impedance of 268.768 ohms. This is the impedance. So we want to find the current. Remember, the formula is voltage equals current times impedance. Impedance is, now I'll define what impedance is. Z is impedance. Impedance is the total resistance. If you take all these and combine it into one resistor. Let's just say this is the battery. If you combine them into all three of these into one resistor, it would be the impedance. It would be a value of this resistor, this many ohms. So voltage is 120. It's 120 volts. We're trying to find the current, and we know the impedance. We calculated it as 268.768. So the current is equal to 120 divided by the answer, or 0.446 amps. That's the current. But are we trying to find the current, or are we trying to find the voltmeter? We're trying to find the voltmeter reading, which is in voltage, in volts. So voltage equals current times impedance. Well, not impedance. We're trying to find the voltmeter reading across the inductor. So that means we want to find inductive reactance, which we did find out, which we found out all the way back here. This value right here. So using the final formula, we can get voltage equals current, which is 0.446, times inductive reactance, which is this number right here, 135.717. So plugging everything in, you would get a voltage of 60.595 volts. So the answer is 60.595, which rounds to C, 60.6. So the answer to number 20 is going to be C, 60.6 volts. And we're done with the 20 questions on the physics section of the exam. And if you had started from biology to chemistry to physics, you'd be done with the entire exam by now. So I hope you found this video useful. As always, make sure to leave down in the comments if you have any doubts that you want me to clarify. I'll be more than happy to answer them for you. And if you think that this video is helpful, it'd be really helpful for me if you would like and subscribe, as that would motivate me to keep making these videos. I hope you enjoyed these videos. I hope you enjoyed this and learned something new from this. And I'll be seeing you guys when I make my next virtual challenge meet video.